I think we can start. I'll begin by starting where I left off last time. So I was beginning to talk about the bracket polynomial. We'll come back and pick up some other loose ends, but I want to have this on record, this discussion. So the bracket polynomial is defined by a recursion or a skein relation, and the formulas look like this. I have a knot diagram with a crossing in it, and I'm going to define for any given knot diagram K, this is going to belong to polynomial ring in A and B and D. These are commuting variables. This will be defined on knot diagrams or link diagrams. And we'll see that it's well defined on diagrams. On diagrams. And then we'll investigate what happens to it under Rademacher. So on diagrams, it's defined as A times the result that you would get by smoothing the crossing this way, plus B times the result that you would get by smoothing the crossing the other way. And if there is an extra loop in the diagram disjoint from the rest of the diagram, then it will multiply by D. And we'll take at the outset the value of it on a loop to be equal to D. Sometimes we normalize that away, make it 1. But that's very simple. And then we need to see that this is well defined, but let's just do an example first. So and we did these examples last time, but let's do them again. A simple example would be a little figure-8 diagram like this, not the figure-8 knot, but then according to the rule, this is going to be equal to A times the result of smoothing it this way, plus B times the result of smoothing it the other way. And that is equal to AD plus BD squared, which I prefer to write as A plus BD multiplied by D. And now you can see one of the advantages of possibly normalizing this calculation as far as a single loop is concerned. If we divide it by the value of a single loop, then everything would be divisible by that loop in the calculation, because there's always at least one loop left over when I'm calculating. You can see that. So A plus BD is the corresponding thing. What would happen if I did it the other way? Well, then I get A times, and now I'm smoothing it this way, plus D times moving it the other way. And that's equal to AD plus B times D. So those are the simplest examples of calculating this that I could write, other than a single loop. Now, before I go further, the convention about which way you smooth and what you did is as follows. You can think of it this way, that you labeled this with an A here and an A here and a B here and a B here. And then you see that when you smoothed it this way, the A's are communicating with one another. And when you smoothed it this way, the B's are communicating with one another. So that's one way to remember which way you want to write A or B, right? Because if you're looking at this, you might be confused at the outset, which way do I write this, A or B? But A is determined by that smoothing that puts the A regions in contact with one another. And what are the A regions? The A regions are obtained by rotating the overcrossing line counterclockwise. And then you see that you sweep two regions when you do that. Sweep those two regions. So those are the A regions. Rotate the overcrossing line counterclockwise. That's just a mnemonic. It's showing you that choosing a crossing really does make a distinction between two of the vertical angles and the other vertical angle. But another way of thinking about it might be that as you approach along the undercrossing line, the A is on your left. So that tells you which are the A regions and which are the B regions in another way. See, if you approach along the undercrossing line, the A is on your left in either case. So those are a couple of ways of understanding which is an A smoothing and which is a B smoothing. And then how does this look if you were actually calculating some knot or length? Well, we did one. So let's do another calculation. I assure you that this is a well-defined calculation on diagrams, and we need to prove that, but let's do another example. Take this one. What will happen here? Well, I can smooth this in an A way this way. That's the A smooth. So this will be equal to A times this guy plus B times this guy. Okay. And now this one, we already worked it out. It's this one here. So that's equal to A times A. Now let's see, the A smoothing guy, AD plus B. And the other one, I'll put the D outside, plus B times. And now what is this? Is this an AD plus B or an A plus BD? When you look at it and say, where's the A smoothing? The A smoothing is this way, which is a single loop. So this is an A plus BD. And then this is all multiplied by. I could simplify that, but I'll leave it. The point is that every time you calculate, you keep doing this recursively, you eliminate a crossing at every point in calculation, or you eliminate a circle. And eventually you eliminate the entire diagram and have algebra in front of you. But why is it well defined? Okay, so let's talk about why it's well defined, and then we'll investigate what happens when you do Rademacher. Well, I'm going to give you a different definition. I'm going to say that a state S of a diagram K is the result of moving each crossing in one of two ways. And usually we label smoothing sites by A or B. By A or B. So for example, take a trefoil knot. Well, let's take a simpler example for a moment. Take our friend the Hoffman. So what are the states? There are 4 of them. I can write them all down. That's why I decided to choose that. So I could enumerate them by just drawing the diagram without having chosen how I smoothed it. There will be 4 of them. 4 ways to smooth the diagram as a whole. So I think I like A better than B, so I'll smooth both of these this way. Those are the A smoothings. Look here. These are A smoothings. Not mistaken. And I'll label them for they. So that's the first state. And then maybe I'll change this one to a B. I'll leave this one as an A. Or maybe I'll change this one B and leave this one as an A. Or I'll change them both to B. Okay, so there are the states. So now and you could, we could draw some states for that. I'll leave it now. Then I claim that bracket K is equal to the sum over the states of, and now I'll tell you what these mean. KS is equal to the product of the A and B labels on S, and norm S is equal to the number of loops in S. Okay. That makes that well defined. And we're claiming, well, actually, this is actually the definition of the bracket. That's well defined, of course. Certainly well defined polynomial in A and B and D corresponding to some diagram. You take the diagram, you enumerate the 2 to the n different states that it has. Let's make sure we got all these right. A and A. Going this way is an A smoothing. And going that way is not an A smoothing. Oh, we got it wrong. Okay. So that one's wrong, then undoubtedly this one's wrong, and that one's wrong. And are these all right? Oh no, I see. I'm doing a bad job labeling. All right, so we have to go back and relabel this. Let's do that while you think about the definition. Okay. Now let's go back. This one is a B. And this one is a B also. Right? Because if we were to, maybe it would actually help to label the regions. We could do that in a different color here for this example. So these are the A regions. And these are the B regions. Over here, these are the A regions, they're local, and these are the B regions. Okay? Better. Now you can just look at it and see, oh, that I still am making mistakes. But now there should be no margin for error. Maybe I didn't make any mistakes, but it's good for you to look at it. So going back to the diagram, I really have labeled the A regions and the B regions there, and the A regions. Oh, I'm not a good morning for doing labeling. All right. We're definite on these. And now what about this one? This is an A this way. And this is a B this way. And the thing is linked the way I've drawn it. Okay, that's what I wanted. Now, I'm trying to draw this diagram. Yeah, okay. Now let's indicate the labels here. This is an A. And this one over here is a B. This one is an A. This one over here is an A. And this one is a B. And this one over here is a B. This is a B. And this one over here, A. When I finally calculate, I want it to come out right. So I hope that's okay now. So now, anyway, it's well defined, and this is well defined. And now what I'm claiming is, let's not do the truffle just yet. So now my claim is that with the state sum definition, the identities for bracket K are a constant. So let's see if we can understand that. I'm looking at a diagram and I have a crossing like this. So this is going to be equal to the sum over states where this crossing is smoothed this way with an A label. Multiplied by an A. Because the A label, I have to keep track of it and I just pull it out. And this will be for K prime, where K prime is the diagram obtained by smoothing it that way. K prime doesn't know about an A label there. But all I have to do is now look at the states of K prime, the smaller diagram, and I get the sum over the states of the smaller diagram, plus B times the sum over states that are smoothed this way, and I have a B, for K double prime, the diagram which has this smoothing, times K double prime S, B to the number of loops in S. So I'm summing over all the states in the original diagram, the ones that are smooth horizontally at that point, and the ones that are smooth vertically at that point, the ones that are smooth A type, and the ones that are smooth B type. Then I get a sum, in this case, over the smaller diagram, all its states, because the state of the smaller diagram is just smoothing all the rest of the crossing. Right? So then, if you write out what I have said, the logic is telling you the formula, because this is A times the bracket for this smoothing, and this is B times the bracket for this smoothing. So we're done. There's the identity. If you went up here and said, I'm looking at this crossing here, then I have these states where I made an A smoothing right there, and I have these states where I made a B smoothing right there. And if you were thinking about the link, then you are thinking about the A smoothing of the link, which is like that. And you're thinking about the B smoothing of the link. Looks like that. And I'm just thinking about it in a slightly different way. I'm saying I could consider all the states, but then there are those states that have an A smoothing there, and then these can go one way or the other, and that's these two, right? So what I'm looking at here is actually the state expansion of this guy. And what I'm looking at over here is the state expansion of the other guy. So that when I write this, I'm actually thinking, the state expansion of this is equal to the sum of the state expansion of this multiplied by an A because I needed an A from that label, and the state expansion of this. So this formula then becomes a statement about the way the states, which add up to give me the bracket, decompose into two disjoint collections. Okay, so that's the proof of the formula on the basis of this, which shows its well-definedness. But it's not just the well-definedness. It will be of use to us continually to ask ourselves, well, what are the different contributions to the bracket as we think about it as an invariant from the states? What can happen, right? And if we understood that better, we might be able to prove some theorems. And there are many things about it that we don't understand well enough. Now, what about having an extra loop? Well, an extra loop next to K is going to be equal to the sum over the states, but those are just the states of K. It's S belonging, S equals states of K for K. Just for K. I don't have to worry about the extra loop. There isn't anything going on. I just sum over all the states of K. And then I have bracket KS because there aren't any labels or anything over here. So it's just the state related to the label. And then I have D to the norm of S, the number of loops in that state, plus 1 because I have the extra loop. But that is saying exactly that this is equal to D times the state sum for K. That's it. And for a single loop, this is equal to D because the formula says sum over KS, there aren't any, and that means just one. And D to the number of loops, there's only one loop. So you just get one state, an empty kind of state, and D to the 1. So there are our formulas all coming out of this state sum. Okay, so now we're clear that it's well-defined. And if we wanted to, we could calculate this way. Let's see what happened if we calculate it this way. Here, let's call this half. And let's calculate half. So according to the state sum, I get AB and BA, so I get 2AB. Oh, I'm sorry. The incoherent here. Let's do it according to the definition. I get ABD. The next one is A squared D squared. The next one is B squared D squared. and the next one is ABD. Then we can factor out a D, and then we get AB plus A squared D plus D squared D plus AB. So I get 2AB times. Now you might compare that with what we did on the previous board by using the recursion formula, but I shan't do that today. Okay, you can see if I made a mistake or not. But if you had copied down what happened on the previous board, then you ought to be able to check this gave you the same thing. Morally, it should. Okay, so this is really a graph theory kind of idea, right? That given the diagram, thinking of it as a kind of a graph, I can define I can make this well-defined 3-variable polynomial associated with the linked diagram, and maybe we could get some topology out of it if we could see how it behaved under Rademacher. So that's our next project. How does this behave under Rademacher? So we already know how it behaves under the first Rademacher proof, but I want to go on to the second one because the second one is the one that gives me the best morals about what to think about. So let's look at how the bracket as we've defined it will behave under the second Rademacher. So that means I need to look at all the states of this or to expand it on both of these crossings. So let's do that. By drawing a little diagram of all the local states. And I still like to draw the A state first. And that's this guy, if I'm not mistaken. Now that's an A. And this is an A. Okay. So that's the A state. And then you could keep this to be an A and let this turn into a B. Or you could take this one and turn it into a B. Or you could take this one and turn it into a B. But turn the other one into a B as well. Well, B. Okay. So those are the 4 local configurations. And so just as before, same argument, we have that that this is going to be equal to A squared times the bracket of this plus ABD, because there's a loop there, times the bracket of this plus AB times the bracket of this plus B squared times the bracket of this. And this means that whatever knot you stick in there, this is a correct expansion formula for the bracket of this with that knot or link stuck into the outside. And the reasoning is exactly the same that we did for the state sum a moment ago. The state sum consists of those states that are smoothed exactly this way here, plus those states that are smoothed this way, plus those that are smoothed this way, plus those that are smoothed that way. And you add them all up. And when you remove the labels, you have these smaller links. This one. Now they're the same. And that one's the same. And this one's different. So I can collect up my terms. And I get A squared plus B squared plus ABD multiplying the horizontal smoothing plus AB multiplying the vertical smoothing. So that's the correct formula for how this would behave if there was a potential Rademacher 2 move there. So it's not invariant under the Rademacher 2 move. It behaves by this formula. And if you were interested in extracting topology from the polynomial, then you could say, well, all right, then what I must do is I must throw away all those polynomials that are divisible by a squared plus b squared plus ABD. And then at least up to a multiple, it would be invariant under the second Rademacher rule. So how do you throw away? One way you throw away an algebra is to mod out by the ideal generated by whatever you're throwing away. And you can do that if you want to. You can take the polynomial ring modulo the ideal generated by this. However, I'm going to take the simpler algebraic notion. I'm going to set a squared plus b squared plus ABD equal to 0 and AB equal to 1. And if I do that, if I find specializations of my variables that do that, well, then it will be precisely invariant under the second Rademacher rule, because this will be 0 and that will be a 1. Now, what happens if I do that? That says B is equal to the inverse of A, and then AB equals 1, and then D is equal to minus A squared minus A to the minus 2, because B is equal to A inverse. So now I have this peculiar looking substitution of values for B and A. B is equal to A inverse. D is this very special value in terms of A and A inverse. And now bracket K. Now bracket K is in the ring B, A inverse. Lagrange polynomials in A. One variable instead of 3. So this is one way to make it invariant under the second Rademacher rule. Then bracket of any diagram with a Rademacher true move is the same as having done the Rademacher true move. It will be precisely invariant. So that's good. I can get an invariance under the second Rademacher. And what would happen under these circumstances for the first Rademacher? So from now on, I'll go to another board, but from now on, bracket K will be equal to 1 over D times the sum of bracket KS, as before, number of loops, and B will be equal to A inverse, B will be equal to minus A squared minus A to the minus 2. So I'm going to have, that means that now will mean this, that we will have A times this plus A inverse times this. Bracket on the loop next to K will be B times bracket K, and the bracket of a single circle will be 1. Okay, so that's what I'm going to have when I write sharp bracket. Okay, and we'll use square bracket K for the 3 variable bracket. Okay, so that's a change of notation, which is natural at this point. Well, I'm going to use sharp bracket to mean the topological one that is invariant under the second Rademacher rule, with the D equal to minus A squared minus A to the minus 2. And the value of the loop set equal to 1 by dividing off one loop. Okay, But I still want to have this other one around. So we're still going to have good old square bracket with its formulas that it's A D and value of the C. I'm still going to keep that around with arbitrary A, B, and D. I may want to point out that it has interesting properties. I may want to ask a question about it. I might want to specialize it differently. But now we're going to continue on with the sharp bracket with the specialization. Because the next thing is just a very nice miracle. We're interested in what would happen under the third Rademacher rule. So we go ahead and try it out. Okay. So it's natural enough to expand on that crossing there on the below. And when we do that, we get A times S plus A inverse times the other one. All right. But it's invariant under the second Rademacher move. So I can simplify this, bring it into the middle. And I can do another second Rademacher move and bring it down below. So this bit of diagram here is equivalent by the second Rademacher move, this diagram, and that's equivalent by the second Rademacher move to this diagram. So I can write that this is equal to A times the bracket where this line goes down there and A inverse times the bracket where the line also is going underneath. And as to whether it goes underneath sort of down or underneath sort of up makes no difference, right? To the state sum, it makes no difference whatsoever. You will just get the same configuration of loops up to their topological type in the plane. And you're only counting them, so it doesn't matter. These are the same, and this is true. But what you're looking at here is the expansion for a crossing that is living above this line that I pushed down. So this is equal to the expansion of this. I'm sorry, I threw it backwards. Expansion, this. So that implies that bracket K is invariant under Rademacher 3. For free. We managed to get it invariant under Rademacher 2, and by the luck of the draw, it's invariant under 3. These are not mathematics, they're explanations. So, so that's good. Now I have this invariant under Rademacher 2 and Rademacher 3, and it's behaving in an understandable way under Rademacher 1. We should go back and look. How does it behave under Rademacher 1? But so far we have it invariant under 2 and 3. What about 1? Go back to the calculation we did before. This is equal to, let's see, when you smooth it that way, you're going to get an extra loop. So this is AD plus B, no extra D because it's gone. So this is equal to A times minus A squared minus A to the minus 2 plus A inverse. And that's equal to minus A cubed minus A inverse plus A inverse was just equal to minus a cubed. O times something, of course, times the bracket without the extra thing. That would be a calculation. And if you get a diagram and you expanded this, you get A times D, and then you get B. So you get AD plus B, but times just a bit of line without any extra curl. So we get minus a cubed times a bit of line without any extra curl. And if the curl goes the other way, well, then it will come out minus a to the minus 3, as I'm sure you can check. So we have these two rules for how it behaves under the first Reidemeister move. It multiplies by either minus a cubed or the inverse of minus a cubed. Now, how do you tell which is which? I like to do it this way. You may also find that there would be some other convention if you would like, but I like to do this. I put a little arrow on the curl. And then I ask myself, is that a positive or a negative crossing? And I have a positive crossing there, but I have a negative crossing here. And this positive crossing that I'm getting from the curl is reminding me that this is a plus 3. And the negative crossing that I'm getting from the curl is reminding me that I'm getting a minus 3. So that's what I do to remember it. You may find another mnemonic that is useful to you. Okay. So now let's do a calculation or two to see what we can do. Let's go back to our Hoffling. And calculate this guy. So I'm going to do the calculation that I did before all over again, I guess. So it's equal to A times the result of A smoothing that plus A inverse times the result of B smoothing it. And now we're going to use our technology. This is going to be A times, what have we got here? We've got a certain kind of curl, and I orient it locally and see it's plus, so that gives me a minus a cubed times a loop, but the loop value is 1. So that's what that is. In other words, we can note that our previous calculations of these are now a little simpler. This is a minus a cubed, and this one here is a minus a to the minus 3. Now, what about this one? Well, let's see, I'll orient it. And oh, it's negative, okay. So that's plus A inverse times minus a to the minus 3. And so I get minus a to the 4th minus a to the minus 4th. And that's my value for the Hoffling. And that's invariant under Reidemeister 2 and Reidemeister 3. So if you wanted to try an experiment, you could mess this up using Reidemeister 2 and Reidemeister 3 and calculate again. You'll get exactly the same result. Then there's the matter of, we'll do the trefoil and then I'll come to normalization. What about, we'd like to make it invariant under all 3 Reidemeister. Let me postpone that for a moment and calculate one more example. So let's take the trefoil. So I can choose any crossing in the trefoil knot and apply the technology, and we get A times, let's suppose it's that crossing, we get A times, oh, there's the Hoffling coming in, plus A inverse multiplied by this. Well, that means I can calculate the trefoil knot. Okay. I put in what I already calculated for the Hoffling. I get a times minus a to the fourth minus a to the minus 4 constant plus a inverse multiplied by, are those positive or negative? Negative. Minus a inverse minus a to the minus 3, they're both negative, squared. And there we are. There's the bracket polynomial for the triphylon. Might as well multiply it out. So I get minus a fifth minus a to the minus 3 and plus a to the minus 7. Okay. And that tells me that the triphylon is very non-trivial as far as 2 and 3 are concerned. And we know that if we were to do Reidemeister ones, why they would just multiply it by minus a cubed or minus a to the minus 3. So we've definitely again proved that the triphylon is non-trivial, but we're going to get much more than that in a moment. Okay. So how do we normalize? Let me go to the next board. But can we memorize this? Maybe I should memorize this so that I can use it again. And given that my memory is short, I will write it down. It's minus a to the fifth minus a to the minus 3 plus a to the minus 7. That's the raw bracket value for the triphylon. To normalize, bracket K, we find f sub k of a to be equal to minus a cubed, the negative rise of k times bracket k, where the rise of k is equal to the sum over c belonging to the crossings of k of the sine of the crossing. K is oriented. So instead of taking an unoriented diagram, I take an oriented diagram, and I'm using the crossing signs. And if I have a positive crossing sign, I take minus a cubed inverse. If I have a negative crossing sign, I take minus a cubed plus. And I multiply by that factor on the front of bracket K. And then there are two things. One, rise of K is invariant under Reidemeister 2 and Reidemeister 3. Rise of K is sort of like linking number, only you're summing over all the crossings, right? So, and it's defined for a knot diagram. So for example, here's the trefoil knot in its usual orientation. And the rise of the trefoil knot is 3. If I took the mirror image of it, the rise would be minus 3. But the rise is not invariant under Reidemeister 1. But it is easily seen to be invariant under Reidemeister 2 and Reidemeister 3, just like linking number was. Okay? So that's a good thing to have around, and we're going to use it for normalization. Second point is to note that bracket K is invariant under Reidemeister 2 and Reidemeister 3. By our work before, it's certainly true. And then the third point that makes it a normalization is that f sub somebody with a little curl of K is equal to F sub that somebody with the curl removed, no change, no change. And the proof of that is easy. Let's just do it. So if we had somebody with a little curl in it like that, and we wanted to figure out, oh, I should have said as a function of A, of course, because the length is down here, F sub K of A. Okay, so I'm looking at F of this, and this is equal to, let's call this K and this K prime, okay? So then we get that this is equal to minus A cubed, the negative ride of K. That part we are getting from wherever this is, somewhere all over that diagram, the ride, I'm adding it up. And then one more ride, and this ride is a +1. So there's a -1 here. That gives me minus the ride of K prime. This is equal to minus the ride of K prime. One more minus sign there, times bracket of this guy with an extra loop in it. So now I'm calculating and I get minus A cubed, the minus W, let's abbreviate that, -1, times, now what happened here? This is a plus, so this is minus A cubed times the result of that. And these are canceling out. This is to the 1. So this gives me minus A cubed to the minus ride of K times bracket K, because this was K, and this is F sub K of A by definition. So we've shown that F sub K prime of A is equal to F sub K of A when K prime goes by a Reiner-Meister 1 move. Okay. So it's invariant under the first Reiner-Meister. I just set it up so it would be, of course, but I'm verifying for you that it works. This normalization works. It works because ride is invariant under Reiner-Meister 2 and 3, and bracket is invariant under Reiner-Meister 2 and 3. So that means that their product is invariant under Reiner-Meister 2 and Reiner-Meister 3. And 3, F is invariant under Reiner-Meister 1. So 3 says Fk is invariant under Reiner-Meister 1, and therefore F is invariant under Reiner-Meister 1, Reiner-Meister 2, and Reiner-Meister 3. So now you see the thing is really working. We have an invariant under all 3 Reiner-Meister moves. So we have an honest link invariant. And for calculation purposes, it makes sense to calculate the bracket and then normalize it when you're done, rather than try to invoke that during the middle of the process. Now, there's another theorem that we need. So any question about that? That's the foundation. Here's a proposition. If K star is equal to the mirror image of K, which all crossings. For example, here's the trephone knot. And here's the mirror image of the trephone knot. Then bracket K star of A is equal to bracket K of A inverse and Fk star of A is equal to Fk of A inverse. Therefore, if K is equivalent by Rademacher 1, 2, 3, a star, if it's equivalent to its mirror image, then it follows that Fk star of A is equal to F, I'm sorry, Fk of A. Ooh. Then Fk of A is equal to Fk of A inverse. If a knot is equivalent to its mirror image, okay, we say K A chiral, not chiral, implies that Fk of A is equal to Fk of A. And if Fk of A is not equal to Fk of A inverse, then A is chiral. Not equivalent to its mirror image. Chirality means inequivalent to the mirror image. Achiral means equivalent to the mirror image. And that follows from this, right? If K was equivalent to K star, then Fk star of A would be equal to Fk of A. These would be the same. On the other hand, it would be equal to Fk of A inverse. So the symmetry of turning into your mirror image means that the polynomial is symmetrical under changing A to A inverse. Interesting, huh? It means that it's quite possible to tell that a knot is chiral by using this invariant, and in fact, we can. So let's see what we have. Here's the trephone knot. And we have that the bracket of the trephone knot, according to our previous board, was minus A to the 5th minus A to the minus 3 plus A to the minus 7. Right? And the rise of the trephone knot is 3. So that says that F of the trephone knot is equal to minus A cubed, the negative rise, multiplied by minus A to the 5th minus A to the minus 3 plus A to the minus 7. And that's equal to minus A to the minus 9. So I have to multiply by A to the minus 9 and change signs. I get A times A to the minus 4, subtracting 9 from 5, plus A to the minus 12 minus A to the minus 16 for the F of the trefoil. And certainly Ft of A is not equal to Ft of A inverse. We flip to positive exponents. So that implies that T is not equivalent to T star. That's our proof using the normalized bracket that the trefoil knot and its mirror image are distinct from one another. Okay? And of course, this leads to a research question. when does, you might say bracket K or FK succeed seeing chirality? There are knots that are chiral that are not seen to be chiral by the bracket. But I don't know, I don't understand a good theorem. I would like a theorem that says, under some circumstances, it will succeed. Or this is the only way that it fails to succeed, but we don't understand that. In general, we don't understand how to completely classify which knots are chiral and which ones are not. Must know. It's much subtler than just telling whether or not it's non-trivial. The Alexander polynomial, which we have begun to mention here, but won't come back to very much, is not able to tell the difference between a knot and its mirror image. But this was one of the reasons why this was very exciting to encounter in the early 1980s, exactly because one had polynomial invariants of knots and links that could tell the difference between knots and their mirror images. Now I have to tell you a little more about what this is, how this is related to something called the Jones polynomial, and how it's related to other things. Let me think what I want to say. How much time we have left today? Okay. So let's do another example. Let's do the figure 8 knot. Now, figure 8 knot is chiral, so we should get a symmetrical polynomial. Here's the figure 8 knot. You've seen it before. And in fact, I wanted to use this opportunity to indicate a little bit of lore about the figure 8 knot in a different direction. Okay, so on this sheet, I have indicated getting the fundamental group to figure 8 knot. It might be a little different from the indication for fundamental group of figure 8 knot that I had used the other day when I gave it to you as an exercise for calculating Alexander polynomial. But it's the same yoga, right? A times C equals D, D times A bar, D bar times A, that's sharp, is equal to B, B times D equals C, and C times B bar equals A. And then we write out the fundamental group relations over there, and then I'm going to keep D and C. I'm going to keep D and C and substitute them into the others, and I end up with only one relation. It was like what happened with the Trefon. Okay. I'll make sure this is in our reference list for you. Yeah, but the point is that you can then write the fundamental group as one relation, and then if you look at that one relation, you see that it can be written in the form of A is equal to W inverse, and W is B inverse A, B A inverse. A very nice presentation of the fundamental group. I believe this observation that it's written this way is due to Bob Riley back in the 1970s, because what Riley realized is something very beautiful about the figure 8 knot. He realized that he could map it to the matrix group, projective special linear group over the complex numbers. That is, never mind the definition of that. He could map it to these two matrices, the A and the B, and then you could map little a to this matrix and little b to this matrix, and then W would be mapped to that matrix, where W is this root unity here, minus 1/2 plus the square root of 3/2i. And then WB, W inverse will be equal to A. So you get a nice matrix representation of the fundamental group of the knot into this group, PSL2C. And then he knows that that tells him that there must be a relationship with hyperbolic geometry. But he's coming to it by looking for a representation of the fundamental group. He knows that this is telling him that there's some kind of relationship between the knot and hyperbolic geometry on the complement of the knot. This is a story which you can look up on the web then from there, because what happened was that Riley did a lot of work on this and began to see relationships with hyperbolic geometry in the knot complement. But along comes Thurston, who's a fantastically good topologist and geometer, and he looks at that and he understands that it's much more general than the figure-8 knot. He understands that very large classes of knots can have geometric structures on their complements, and gets a whole theory out of it. But that whole theory starts from Riley's trying to understand the fundamental group. So this is a good example to look at because it shows you how non-obvious the fundamental group is, as we said before, but that someone might make a good observation and find an interesting representation of it. And such representations might reflect on the geometry of the complement because the fundamental group has to do with the loops in the complement of the knot. So I wanted to show you that. But we're over here doing the bracket, which is quite different. And the other research problem that comes up here, and we really don't understand this at all, is that we have to find, in finding the bracket and the Jones polynomial and things like this, we have found another way to get non-invariance that's really different from things like fundamental group. I mean, you get a polynomial out in the end if you're calculating Alexander polynomial, but when you do it by working with the complement of the knot, you're doing something rather different from the combinatorics by which we define the bracket. So in fact, we do not know how to derive the bracket from the fundamental group or from some augmented version of the fundamental group. We have no idea. The bracket and those kind of invariants seem to be very different from what goes on when you're examining the fundamental group. And yet, nevertheless, there are relationships between this kind of thing and fundamental group, but they're lying deeper. Now, come back to this. We want to calculate the bracket of the figure-8 knot. That's easy enough for us to do. Here's the figure-8 knot. But I'm telling you that the figure-8 knot is equivalent to the mirror image of the figure-8 knot. So let's concentrate on that for a moment before we calculate the bracket. Can you see that this is equivalent to its mirror image? Well, there are lots of ways to see it. Let me illustrate one. I'm going to swing this arc all the way over here. So this is certainly equivalent to that, by which I mean Rademaster 1, 2, 3, or ambient isotopy. You can swing the arc, right? You can do it by a whole bunch of Rademaster moves. Or you can think of it as sitting on the surface of the two-sphere, in which case you swing it around the back. But now look at this again and see that there is some analogy between this loop, which is going here, and this loop, which is going here. And two crossings. So if I label this crossing A and this crossing B, then this could be A prime and this could be B prime. And now you see that I can deform this, and after I've deformed it, it looks like this. And then, down here. So I'm just pushing it around in the plane. So I push this guy upward, and the A prime goes from upper left to lower right, and then here, and then you have the loop going around this part, and it goes over first and then under, and that's it, right? So that's equivalent to that. But this is the mirror image of that. Here is figure 8 knot, and here is the mirror image of the figure 8 knot. So the figure 8 knot is equivalent to its mirror image. Good. So that's the first chiral knot. First non-chiral knot is the figure 8 as the trefoil knot, very first knot. The very next knot in the table is equivalent to its mirror image. So, so now let's calculate the bracket of the figure 8 knot. Well, what about the rise of the figure 8 knot while we're at it? Plus minus. So the rise of the figure 8 knot is equal to 0. So what about the bracket of the figure 8 knot? Well, I can expand on this. Oh, I want the figure 8 knot. It's over there. So I'm going to expand on this guy here. So that will give me A times this plus A inverse times that. I'm making a mistake. Partly because the figure 8 knot picture closer to me so I could refer to it. All right. So that's that again. Now, I was doing the expansion, and I wanted the A, and that's the A, and now we want the B. Okay. Good. Happy? I think I'm happy. All right. How about, look at that. This is a trefoil knot. And this one is a Huffling. So, and then there's a little curl, and I have to keep track of that. What kind of a curl is it? It's a positive curl. So I'm going to get A times minus A cubed from the positive curl times minus A to the fourth minus A to the minus fourth. We're getting better at this, right? Times the Hoflink evaluation, which by the way, didn't depend on the mirroring. And then we get A inverse. And then is this the positive trefoil or is this the negative trefoil? Better check. It's the positive trefoil. And according to my reckonings, the bracket of the positive trefoil is minus A to the fifth, minus A to the fifth, minus A to the minus 3, plus A to the minus 7. So we're putting that together. We get minus A to the fourth times minus a to the fourth, let's do it in our heads. I get minus a to the fourth times minus a to the fourth, so that's a to the a. Then I get minus a to the fourth times minus a to the minus fourth, that's a 1. Then I get minus a to the fourth. Then I get minus a to the minus 4. And then I get plus a to the minus 8. So putting things together a little bit better, I get a to the 8 plus a to the minus 8 plus 1 minus a to the 4 minus a to the minus 4. And this is bracket E, but it's also equal to F because the ride is 0. And you see that it's symmetrical in the substitution A to A inverse, as it should be, because E is chiral. E is equivalent to its mirror image. The polynomial has to be symmetric in A and A inverse. So it is a relative of the trefoil knot, which is chiral. There's chirality in it in some sense, but by the time you put all that together in the right way, the chirality is gone, and the trefoil knot ends up being achiral. And you can go on up the tables and try other knots and see how they behave. How bad will that kind of an exercise be? Not too bad. Let's just, we're of course not going to calculate much more today, but if you wanted to calculate, let's look at the tables and ask yourself, what would it be like to go up the tables and do a few more calculations? We've done 3 and 4, 3, 1, 4, 1. You could do 5, 1. If you did 5, 1 and you wanted to see what would happen to the bracket of that, it would go down to an unknot if you smoothed it one way, and if you smoothed it the other way, it would go down to trefoil. Similarly, 5, 2 wouldn't be hard. You could go all the way up to 6, 3, for example, and get some polynomials. Not a bad exercise if you wanted to do some homework. If you, on the other hand, wanted to find the bracket polynomial of, say, 924, well, then it's going to be a longer matter, and you might want a computer program to do it. So, in the interest of doing something in the last few minutes, let's discuss that. There's a good deal more I want to say about the bracket, but let's talk about how you would make a computer program for this. So if you have a knot and you would like to code it so that a computer could handle it, then one way to do that is to label, this is coding we're talking about. One way to do that is to label all the edges in the graph. So you look at the underlying graph and label all the edges there. So maybe I label them by small letters, but these are rather different labels than the ones that I was doing before, where I labeled arcs in the diagram. I'm labeling edge labels. And if I made edge labels here, then I would see at a crossing, I would see some edge labels. And then I want to discriminate between an unoriented crossing like this and an unoriented crossing the other way. And I'm going to do that by taking a little tuple. I'm going to take the cyclic order counterclockwise, A, B, C, D, starting from the overcrossing point. Okay. Now, if I switch the crossing, still A, B, C, D, then that means that the code I use starts in B, B, C, D, A. So you see that one cyclic permutation will switch the crossing. Now, this is going to be equivalent from my point of view, unoriented diagrams. These are unoriented crossing codes. If I had started with C, C, D, A, B. I don't care. And this one is the same as D, A, B, C. So you see, if you did two permutations, take A around and then take B around, you would arrive at the same thing. And that makes sense because one permutation is going to flip the crossing, and you do another one, you flip it back. So these two codes, it doesn't matter which one you write. So that means that if I'm over here with the truffle knot, I can write my codes. I have A, B, C, B, C, D, and I'm going to write three codes. I'm sorry, E. Every edge is supposed to have a label, F. There. Now every edge has a label. So I go to the first crossing, and I have E, B, D, A. I go to this crossing, and I have A, D, F, C. And I go to this crossing, and I have C, F, D, E, D, E. So there's an abbreviated crossing code for the diagram. If somebody handed you that crossing code, I'm not bothering to write the parentheses, but if I'm going to give this to the computer, I may need to write parentheses. And I might have to put a header on this if I'm doing Mathematica in order for Mathematica to know what kind of a list it is. But if I'm doing it by hand, I just write that. This encodes a truffle knot. Somebody says to you, EBDA, and you write down EBDA, and they say to you, ADFC, and you write that down, and they say to you, CFBE. Write that down. And now your mandate is to find the knot. So you go to this crossing that you've written and you see, B must connect to B. C must connect to a C. D must connect to a D. E must connect to an E. And F must connect to an F. You reconstruct the knot diagram, and A must connect to an A. Reconstruct the knot diagram, twisted a bit because you didn't draw the crossings as nicely as the person who originally drew it. But you reconstruct it. Okay, so this code actually tells you the knot diagram, but tells it to you in a way that you can hand it to a computer. So this is worth your while experimenting with. Like, try this translation back and forth, see it working. Crossing codes are very nice. And then what would the crossing code equation be for the bracket? Well, it would be that the bracket says this is equal to this plus this. I suppose you had A, B, C, and D. Well, then you have a B and C, and an A and B. I'm thinking of labeling the N, right? And then you have a C, a D, and a B and an A. So you're going to have to say something like A, B, C, D is equal to A times delta CD delta BA plus A inverse times delta CD delta BA. And the deltas are going to have to formally behave as though C was equal to B and D was equal to A in the computer, right? So that's what you have to do. You have to tell the computer that you're going to expand these symbols into these symbols. If you have them not, it would be written as a product. You would have E, B, D, A multiplied by A, D, F, D multiplied by E, F, D, E. Then you tell the computer expand these according to a formula like that, and suddenly you have a bigger thing. And then you have these deltas, and the deltas should behave like this, right? Suppose you had a delta A, B, C. Suppose that happened. Then you would have a delta AB and a delta BC. And you would want this to be equal to a delta AC. And if you had somebody that went around like this, you would have a delta CC, and that should be equal to our value D. So you tell the computer these things. You tell it expand, use your polynomial capabilities to multiply these out. When you see a product of things like these, then you have to collapse them together until they become single loops. And the single loop value, when you finally get it, is a D. And then the computer has proceeded to compute the state sum. So what does that actually look like? This is where we'll end today. Let's look at what the program looks like. So in Mathematica, which is when it's working a very concise language, that bit of code at the very top of my slide is the program. You see what I wrote? I wrote X bracket. It needs an X at the front in order to know what it's doing. ABCD is delta AD, delta BC plus B times delta AB, delta CD. That's this, possibly with some permutation of letters. Okay, then delta AB times delta BC is delta AC. And this is basically saying delta of something with one label is equal to the D. And then you tell it, do these rules again and again until you can't do them anymore. And that's the raw bracket involving A, B, and D. And then if you allowed B to be equal to A inverse and D to be minus A squared minus A minus 2, rule 4, then you can apply rule 4 and get the actual bracket. And then you see how it is going to go. You put something in here that's a more complicated thing than I had in mind. And then it will calculate this stuff for you. And let's demonstrate it on what we were just doing, for which purpose I need EBDA and so on. So let's put it in and run the program. It's working, so I have to tell Mathematica to initiate that. Then paste right an input. So and then graph file equals X bracket, X bracket, X bracket, and then our codings were EBDA, ADFC, CFB, and we would like we would like the raw bracket,
And we would like, so let's see what happens. Okay. So did you see what happened there? We got minus a to the minus 7 plus a to the minus 3 plus a to the minus 5. And that's our bracket for the trefoil. And this is what happened if you did the 3 variable polynomial that we were talking about earlier without doing any reductions. So with a program of this kind, you can take a larger thing and calculate this, and so you can investigate this invariant for very large knots up to a point. But of course, you see that there are going to be computer problems with this after a while, because you double, it's 2 to the n states. And this formula that expands this doubles every single time. And so if you gave it a knot of 50 crossings, you would be looking at 2 to the 50th states, and the computer would have a lot of trouble. You have to find some shortcuts, break it up into smaller pieces and calculate them, and then put them back together to get the evaluation for the larger knot. So this is a good place to stop today, and I'm going to go on telling you more about the bracket and how it turns into what's called Khovanov homology in the next 2 days.